All right, good morning. So we're going to talk about conic sections today. It's chapter 10. So the first one, I think the last one are kind of new for us. The middle one is parabolas, which is a different look at parabolas, but the same thing. It's going to be pretty straightforward. So what is a conic section? And let's go over that first. So a conic section, the Greeks had cones, and two of the Greeks there, that was a cone. But there's two of them. Like, I know, that's what the Greeks had. And then what they did was they would take little slices out of this. Okay, so if you put a plane like directly through it, and you look at like what's the cross section, right? You're going to get a circle. All right. If you make that plane a little bit tilted, right, you're going to get a circle that's elongated. You're going to get an ellipse. All right. If we take that circle and do that one, if we take that circle and just slice a piece off the corner like that, piece off the corner over here, the resulting shape here, right, is going to be a parabola. Okay. And then finally, I'll do the darker one. Finally, if you put the plane and you cut it, you slice it vertically, you're going to get two pieces, right? And these are called hyperbolas. Okay, hyperbolas always come in pairs. Sometimes the physical application, you only really need one of them, but just realize that there's like a shadow one or there's one that it's still mirrored. It just may not show up. Okay. So today we're going to mostly talk about circles and ellipses. Okay. Next week we'll talk about parabolas and hyperbolas. Okay. So there is a very nice discussion in your book that talks about how to set up an ellipse, and I would urge you to read that. You don't have to understand every step in there. I won't quiz you on everything that's going on with that. But the idea here is if we have, right, we're going to have like 2 points here, okay? And these are called the foci. And the way that we have an ellipse is you're going to tie a string from each of these points, right? You're going to tack down a string to each of these points and pull it and attach it to a pencil, and then trace out like what's the maximum distance away that you can. Okay, whatever the maximum distance of the string is, you're going to go ahead and do that. So this one will be not so tight, but this one will be very tight when we're over here. Okay, and then conversely, when we're over here, this string isn't going to be very tight, but this one's going to be taut. Okay, and that's the idea, is that we're going to trace both of these things out. Okay, so every point on the, and your problem number, I think 3, 4. 4 has you go through and calculate out some of the distances here. So you should see that the distances between these 2 points, right, is the same as the distance between these 2 points. We might do this one today. But the idea is that, if you think about these as the different strings, right, when we whatever the maximum distance is for just this one to here, those are going to be your vertices. Okay. So, yeah, we're going to be talking mostly about how to graph these things and what's going on with like standard forms and how to put everything together. All right. So, like I said, the book does a much better job of laying out the geometry of what's going on than I do. They do lots of pictures. Okay, so I urge you to go ahead and go through and read. It was actually they actually do a really good job. I mean, it's rather clever when they get down to the end. So it's always a good thing to do, to kind of take a look at that. You don't have to understand every step and every piece. You're never going to have to recreate this, okay? But understanding like how we got this is kind of a neat piece, okay? And they show up pretty regularly, okay? Like orbits are elliptical, okay? So you're going to see these. We build things that are elliptical. You're going to see this quite a bit, okay? So yeah, like I said, they do a much better job because they have good artwork to go along with their descriptions, and it's very helpful. So that's what a conic section is. Okay, there's 4 of them. In Calc 3, you get to do them in 3 dimensions, so it's fun to do them now because they're a little bit easier. But we will do this in 3 dimensions eventually as well. Okay, so we start off with circles. Okay, we just start off with circles. I think you saw these in college algebra. I know that they move things around, and you may not have seen them in college algebra. But the notation and the skills that we did for circles, we're going to review them, are going to be reapplying, or we're going to reapply them here. Okay, so if I look at number 1, we just got to get started with that as a working example here. Okay, and we have x minus 7 squared plus y minus 6 squared is equal to, what do we have here? 4 is equal to 4. So going back and remembering, like, okay, how did circles work again? And this, by the way, every conic section is going to follow the same pattern, okay? So we have x minus h, that's horizontal, okay, plus y minus k. If you look up Greek for vertical, Google Translate, you're going to find that it starts off with a kappa. Okay. H doesn't. If you look up horizontal in Greek, it's going to start with a theta, I think. So you know, they don't quite translate over, but since H wasn't busy, we'll go ahead and use that. Okay. So yeah, the center of the circle is HK. Okay. Now this is one of the more confusing pieces here, is because the H and the K, right, the negative sign here belongs to this formula. This is not something you get to come with, right? So for example, if I had an x plus 1, you say, wait a minute, is 1 the center? We'll just do y squared is equal to 1. No, it's x minus a negative 1 squared. That's how we get the positive. So you have to remember, this negative belongs to this formula. This negative is the center part. Okay, so this circle, the center will be -1, 0. Okay, because y doesn't have anything with it, right? We have y minus of 0 squared. Okay, so the k here would be 0. The k for this one, negative of a negative, in order to make this positive, to get -1. This one that they gave us for the first problem is very nice and straightforward. They don't have to do with any of this. Okay, but I noticed that with students, this is a big thing, is that they tend to forget that you know, the negative is part of the formula. So that's something we have to remember. Okay. All right. So next thing is, this is the radius squared. Okay. So that's not the radius, it's the radius squared. We have to take the square root of this in order to get the radius. And it is going to be similar for ellipses, but not quite. All right. So when we get to that, I think we'll do like 1 or 2 of these, then we'll move on to doing an ellipse. All right. But there is a standard form for an ellipse, and you know, it tells you what the axes are. Okay. So let's see here. All they want to know, right, is the center for this one. That's not so bad, right? We just read this one off. So x minus 7 squared plus y minus 6 squared is equal to 4. The center is just 7, 6. Okay, and my radius is 2. Okay, so my center is 7, 6. Oh, that's 76. Oh, you're not going to play with that today. All right. And then part 2, radius is 2. So nice, gentle warm up to conic sections here. Okay, we're doing well. All right. 2 I thought was pretty easy. Yeah. They're not always going to be nice numbers. Okay, that's one of those things to remember as well. All right. Okay, I went like 4 is the distance thing. 5 is going to be good. Nope, we'll have to do this one. All right. Now, the other thing that we have to remember is, and again, this skill is going to be useful for all the conic section problems that you have. All right. And that skill, that technique is called completing the square. Okay. Complete the square. All right. This is one aspect, but I know I don't teach this as well as I should, as far as conic sections as a whole, because I noticed that when I was absolutely turned around and screwed up on something, I tend to have a little bit better way of putting it together for people. But conic sections, I was like, wow, this is so neat. I just never really had much of a problem for them. So I know there's a lot of formulas with this one. I'll try to, to give you guys ways of remembering them. But like way back, I don't know. Okay, you can go to YouTube and look at this one. It's timeless. I don't know. It's one of those things they showed us in elementary school, and it was old when I was in like 4th grade watching this thing. But they do a thing on conic sections in Donald Duck and Math Magic Land, and if you have some spare time to watch that, I would. It's cute. If you have a little kid, you have to babysit your own child, younger sibling, turn that on for them. I don't know. But maybe it'll backfire because my niece is not a big fan of Schoolhouse Rock, and I thought those were awesome. Okay. Okay, we have to complete the square. So in order to complete the square, what we're going to do is you're going to identify the middle term, right? We have ax squared plus bx plus c. And we also have an ay squared plus by plus c. Those are different a, b's, and c's. But we're going to identify the middle term as -2. We are going to take half of it is equal to -1. And then we are going to square this. So we get b over 2 squared is equal to 1. Okay. So here's what's going to happen. We have x squared minus 2x plus 1. But what we're going to do is we're going to balance the equation by putting the 1 on the other side as well. Okay. Plus y squared. Now, this will factor. If we have done this correctly, this piece here will now factor because it's a completed square, right? Complete the square. That's the whole point. And the best thing about this is no matter how horrible this looks, this b over 2 term, that's what it factors into. So this -1 here and that -1 there, those are the same -1s. All right. So even if I go off the rails, and I will, I'll show you an example in a second here. It's like, oh, that's terrible. Like, yeah, but you can impress your friends. You can factor that no problem because you know what the secret is. Okay, so x minus 1 squares plus y squared, and that is equal to 171. Okay, so in this case, what's the center? Right, the center is, remember, the -1 belongs to the formula, so that's 1. This is y minus 0 squared, and that's my center, and my radius is equal to the square root of 171. Well, let's see. Can I go fishing for some perfect squares and make this a little bit better? 171 is not a perfect square, though, so whatever we come up with is going to be a mess somewhere in here. Okay, but it should go. What am I doing? Oh, I can't do that. It's 5. That's terrible. Okay, so 3 goes into 171, or yeah, 57 times, and 3 goes into 57, 1, oops, what am I doing tonight? That looks like 19, right? So, okay, so this is 9 times 19 to be 171. Yeah, yeah. So this is, since this is 9 times 19, we're going to take the square root of that. So that's square root of 9, which is 3, and square root of 19, there's nothing I can do with that. So we're stuck. But that's going to be my radius. I have a feeling if I type in square root of 171, it's going to yell at me and say, that is not in reduced form. You should go ahead and do that. So it doesn't want the decimal. It's going to want 3 root 17, or 3 root 19 rather. So the equation in standard form, right? We have, this is what they mean by standard form, x minus 1 squared plus y squared, okay, equals 171. And does the, so let me talk about the degenerate case. I'm glad they put that up. So the radius is, this thing on the other side here is r squared. If we were to get like an x squared plus a y squared equals a -4, go ahead and take the square root of a -4. It doesn't work, right? Not on the real plane, not where we're going to be graphing this. So this is not a circle. Okay, it's what they call it the degenerate case. X squared plus y squared is equal to 0 is also the degenerate case. There's one point that will deal with that. Okay, there's like an inside-out circle, and then that's technically the only degenerate case. This just doesn't exist. This does exist. It has one point, which is a very boring circle. Okay, but we can't graph it. It's just that point 0, 0. So there's going to be times when you're going to be faced with something that is presented to you as a circle, but they lied to you. It's not really, okay? But they give you the option of answering as a degenerate case here, all right? To my knowledge, I don't think your book lies to you very often, so that's my center. And then R, right, is that they're going to want 3 root 19. Actually, you know what? I'm going to type in the square root of 171 and see what happens. Just to see. Oh, all right. I went way out of, okay, I did way too much work then. So please don't, you can do that if you'd like to. I like to because it makes me happier. But, if you don't want to do that, if it's not going to complain, then you are at your liberty to type in this thing without having to simplify it. Okay, which kills me a little on the inside, but there we are. Okay. All right, so that's 1, 3. Those are circles. Okay, now we're going to get into ellipses. So I'm going to let you guys pull number 4 on your own. If you guys want to see it, I'll do it, but let me know. If we're going to look at number 5, what's going on with the ellipse? Okay, so the notation for this, the terminology for this gets a little thick. Okay, this gets a little into the weeds as far as the notation goes. Not the notation, but the vocabulary. And there's certain things that we're going to find out about ellipses. And I got to tell you, I used to work in in doing satellites, and there are words that I worked with putting satellites into orbits. We never used the word eccentricity, and they're going to have us figure out eccentricities. Do not worry about memorizing that formula. I will never ask you that, or if I do, I will give you what the formula is. Okay, so there's stuff in here that's going to have you do the formulas, and even working with things that were in orbit, I never had to deal with an eccentricity. Okay, I'm sure the astrophysics people, I'm sure some people do use it, but it's so specialized and it just doesn't pop up until we need it. So this one, x squared over 4 plus y squared over 5 is equal to 1. let me tell you how we're going to graph these things. We're going to set x equal to 0 and solve for y. And then we're going to turn around and we're going to set y equal to 0 and solve for x. Okay, we're going to do this a lot, okay, because hyperbolas are going to work the same way. This is called method of intercepts. Remember, we have x and y intercepts. Okay, this is what we're doing. All right. The major axis is the longer of the axes. Okay, so the major axis, and I'm not going to ask you this. Okay, this is not a vocabulary term you would have to know. So major axis, this is the long one. Okay, and then they have the minor axis, and it's the short one. Okay, with a circle, both axes, the x and y direction, both axes are the same distance. So that's, why it's a circle and not an ellipse. Okay, so we have x squared over 4 plus y squared over 5 is equal to 1. Set x equal to 0. Then we get 0 plus y squared over 5 is equal to 1. Y squared is equal to 5. And my length, right? Well, not my length, but how I'm going to graph my my axes in the y direction is I'm going to put, right? I'm going to go, x was 0. So we're going to go up here with the square root of 5. Right? This is the point, 0, root 5. And then we also have a 0, negative root 5. Right? Next step is that we're going to set y equal to 0. Okay? So we have x squared over 4 plus 0 is equal to 1. X squared equals 4. X is plus or minus 2. So this was 2, 0, negative 2, 0. Which one of these is longer? Right? Is 2 root 5 longer or shorter than 2 times 4? Right, and I got 2 of them because we're going in this direction, root 5, we're going in that direction, root 5. So it's root 5, right, minus negative root 5 here. That's how we got 2. This one minus that one. So which length is bigger? This one is, right? So the major axis here is in the y direction. That's what they want to know here. Okay, the major axis is the vertical one. Okay. So if you forget, like, how do I do this one again? You can just start plotting them, because I find it easier to plot and to graph these than I do to try to remember all the details that they expect you to remember. Okay, just wait. We have even more formulas. By the way, for the PreCalculus, the face-to-face class that I teach, for the foci and some of the formulas we have, like eccentricity and some of the other things, like, I will write down the formulas for you. I don't need you to memorize those. All right. Like, if you're going to go into, a set of physics where you're studying a lot of orbits and you need to know this, you're going to know. For everybody else, we're going to have time to look them up. All right. This is not information that, like, nobody has ever asked me, like, you're in the middle of Calc 3, like, we need to know the foci for this ellipse. Like, it's never come up, ever. So, except in the class where we did this. So for the second one, okay, we could do the same way. We know this one, right, was 5. That was the one, so this one's going to be horizontal. But let's just work through it for the sake of trying it. Okay, so we have x squared over 5 plus y squared over 4 is equal to 1. We're going to set x equal to 0, solving for y. So we have y squared over 4 is equal to 1. Y squared is equal to 4. Y is equal to plus or minus 2. Okay. Then we're going to set y is equal to 0. Oh, sorry. Yeah, so y equal to 0. So we have x squared over 5 is equal to 1. All right. And then we have x squared is equal to 5. X is equal to plus or minus 5. So again, if I was going to graph, by the way, this is it for graphing ellipses, right? this is your main skill right here. Okay, we're going to do this a lot. Which one is longer, right? The root 5s are longer. So in this case, this one, the axis is horizontal. And then we're done, right? All right, let's try something a little bit harder. Okay. All right, this is the whole, you know, I don't know if you took college algebra in this book, but if you did, because we just covered it in college algebra, we had to graph parabolas, and they asked, where's the vertex? Does it open up or down? What are the x-axes? What are the x-intercepts? What are the y-intercepts? Graph it, and then we had to figure out, like, what's the axis of symmetry? What is the minimum or maximum? What is the domain? What is the? They asked us everything after that. It's going to feel like a lot like that. All right. But again, I need you to be able to identify like the endpoints, because that's how we're going to graph it. And then after that, like, you know, like identify the foci. I will write this formula down for you. Okay. Once we've graphed it, like determining the lengths, this is not a big deal. Okay. It looks like there's a lot of work, but a lot of it's redundant. Okay. So we'll work through this one here, parts 1 through 8. Oh my God. All right. So like a circle, okay, what we're looking for in an ellipse, right, is x minus h squared over a squared plus y minus k squared over b squared is equal to 1. That's your standard form for an ellipse. I know it feels like a lot right now. Once you start graphing them, it's going to be a lot easier. All right. So my center, right, is HK. I think by and large, most of the times your centers are going to be 0, 0, because even if it isn't, you're going to draw your coordinate system so that the center is 0, 0. Okay. So if you're working in an engineering type of a problem, if you can change your coordinate system to make the center of the ellipse the origin, you should probably do that, unless there's a reason why you can't. All right. So the center is HK. In this case, there is no extraneous stuff here, right? The center on this one is just 0, 0. So it's an ellipse centered on the origin. Okay, so that's fantastic. A and B. Now, I know different books do this in slightly different ways. Some books will say to you that A is always the major axis and B is always the minor axis. I'm not really sure the way your book does it. So I'm going to write them in to do my A and B, but I expect to be wrong. Okay. So it's 9 and 7, right? Because that's the square. That's A squared would be 81. And b squared would be 49. So we have 9, we have 7. Okay. By the way, I will not ask you like which one is A and which one is B, because you'll see as soon as we have to identify like the vertices or the endpoints of the minor axis. Vertices are the endpoints of the major axis. You're going to ask this question anyway, and I don't really care if you call it 1A and 1B. All right. The vertices. All right. So when the center is not at 0, this is a little bit harder to deal with, but the vertice is the major axis. Okay. That's one axis. Okay, and they're just going to be ordered pairs. Okay, so same thing. We have x squared over 81, y squared over 49 is equal to 1. Set y equal to 0. All right. So we're going to get x squared over 81 is equal to 1. X squared is equal to 81. X will be equal plus or minus 9. Okay. What's the center? The center is 0, 0. So my vertices are going to be -9, 0, right, because that's the x value, and positive 9, 0. If the center was offset, then this y value, this 0 here, would be the y value. The 9s would be from the center. Okay, so it would be negative 9 plus h, 9 plus h. Okay, we'll do one that doesn't have a 0 center soon enough. But for now, just realize that the center's not at the origin. This is a little bit harder to track, but not by much. Okay, so we have minus 9. Oops, not 0. 0 and 9, 0. All right. So that's very good. The minor axis, the other one, right? So x, right, we set y equal to 0. Now we're going to set x equal to 0. See, we take turns. So we get 9, y squared is over to 49 is equal to 1. Y squared is equal to 49. Y is equal to plus or minus 7, right? So this is the y values. So we are at 0, again, because the center was 0, 0, 7, 0, minus 7. All right, so that's my minor axis, the smaller one, 0, 7. And but the book is not going to care which order you put these in. And by the way, that's all you need to graph this thing. Okay, we are done as far as graphing. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 2, 3, 5. 1, 2, 3, 4, 5. 1, 2, 3, 5. Oops. Okay, there's my coordinate axis with my little x and my little y's. Right, so we have 9 and negative 9. We have 7 and negative 7. Now we just have to connect the dots, and I'm going to say pretend this looks like an ellipse. All right, that's terrible, but that's okay. You don't have to be perfect with this. All right, but that's my ellipse. All right, that's the ellipse. We have everything we, that's pretty much the end of the problem as far as that goes. All right, where are the foci? Again, I have, outside of doing a conic section, a conic sections chapter, I have never been asked for the foci. Okay, the foci is where C is. Okay, C is equal to a squared minus b squared. Okay, I don't have a problem handing you that formula if I ask you where the foci is, because, like I said, this information has never come up for me outside of this section. So this is going to be c squared is equal to 9 squared minus 7 squared. The big one minus the little one. All right, so they have to be reversed. Okay, please reverse them. So we have c squared is equal to 81 minus 49. C squared is equal to, what is 81 minus 49? What is that going to be? 81 minus 50 is going to be 31. 32, because I have an extra one here. Let's see, 8, 7, 11, yeah, 32. Okay, so C is equal to the square root of 32. And again, this kills me to leave it like that. So this is 4 root 2, plus or minus. Okay. And again, they're along the center line. So 4 root 2, right, square root of 32 is 5-ish, 6-ish. So your square root of 32. All right. They lie along the major axis. Okay, and that's where your foci are. Okay, so it's important to be able to, spit these out for the book for doing your homework. I will, if I ask you, I will write down that formula for you. I do not need you to memorize that. Like I said, even working with Okay, you're going to track the satellite orbit. Yep. Like, where are the foci? Don't care. Okay, here's the equation of the ellipse. That's what we're going to work with. All right. Length of the major axis. Okay, you can count them, right? You know, they go from 9 to -9. It's 18. All right. Length of the minor axis. And again, we're going from 7 to -7. So 7 minus -7, 14. All right. 14. All right. And then we have to graph it. All right. They're going to make us graph it. So I wonder if they'll just let us place the center. Oh, yeah, they will. By the way, they didn't give me a little tooltip here to plot a point because this one's pretty easy. But if it's going to be more complicated, they're going to put in the little tooltip to let you plot a point. And the same idea is we're just going to see 7, 8, 9, and then 1, 2, 3, 4, 5, 6, 7. There. It wasn't too bad. Right. And that's all that we're going to do. That we're going to repeat this system, repeat this process quite a bit. Right, but that is how you graph an ellipse. All right. So I think I'm going to leave us there because I think that's probably been long enough to go through this. So this is 1, 5, and 6. Could I have written this down somewhere? 1, 5, and 6. We will 1, 3, 5, and 6. We will do more of these Monday, but they really are like this kind of thing over and over and over again. Okay, and when we get to hyperbolas, it's going to be the same thing over and over and over again. Okay, slightly different formulas. So you have a lot of chance to practice a lot of these problems. So please don't get overwhelmed with what we're working on right now. And you know, by the time we get done with chapter 10, you are going to be a pro at this. Okay, so you're going to look at these problems and you're going to say, oh, they're so boring. Yeah, they are, but they're really kind of cool too. So I'm going to go ahead and leave us there. All right, so take care with that.